Good morning, everyone. My name is Jeona, and I'm currently working as the postdoc at Georgia Tech. Today, I'm excited to talk about our research, securing data analytics in Apache Spark with fine-grained policy enforcement and isolated execution. This work was mainly done by Byung-Ok Kim and me, and advised by Professor Adil Ahmad and Byung-Young Lee. So let me start with Apache Spark. Since introduced in 2012, Spark has been a state-of-the-art framework for big data analytics. Especially running Spark on cloud, so-called cloud-based Spark, has been a tempting approach for collaborative big data analytics. So the data owners who often do not have sufficient infrastructure and labor power can easily deploy and manage their data on the cloud, and the data users who do not have large amount of data can easily access and analyze the shared data in the cloud. For these reasons, many cloud vendors are already providing Spark as a service, such as Databricks, Amazon, and Azure. However, naively employing cloud-based Spark has a risk of violating data owners' expectation. Once the valuable data is handed over to the cloud, untrusted bad actors can access and breach the data. For example, untrusted cloud providers can easily access and leak the data, and also the malicious data users can violate the owner's expectation while analyzing the data. The more problem is that such data often contain private information, and they are under strict privacy regulations. For example, clinical data such as genome and medication history contain large amount of private patient information, and the financial data also include long history of bank customers. And for these reasons, such data are under strictly regulated by privacy laws such as GDPR, CCPA, and HIPAA. And we can already find many real-world cases of the companies being sued for violating such regulations. For example, Nebula was accused, and Walgreens has been also accused, and there are many other cases. And we can also find many articles complaining that the strict privacy laws are hindering the potential of data sharing. So what we want to do is to allow the data owners to avoid regulatory violations while sharing the data. So we propose a new architecture of cloud-based Spark for secure data analytics. So we basically redesign the Spark, but we keep for the usability, we keep the same Spark interface so that the data users can analyze the data as before. But we also improve the security by assuming both the data users and even the cloud providers can be compromised. Even in such environment, we keep the security by preventing any data breach or violation of the policies given by data owners. So to this end, we found two security requirements. But before explaining this, let me briefly explain the internal of Spark. So the data users are to analyze the data users develop their own Spark applications. So in the application, the user's code running by interacting with the Spark libraries. And the library simplifies the distributed computation. So while the application is running, the library internally builds a Spark plan, which is a blueprint of the data analysis procedure. Then once the Spark plan is constructed, it is split into multiple tasks which are executed in the distributed node. Then the final result is returned to the application, to the data users. So to secure the data analysis procedure, we find that we have to ensure the confidentiality and integrity of the entire data analysis pipeline. But also, even on top of it, we also have to ensure the Spark plans constructed by data users respect the owner-defined policies. So let me explain these requirements with the possible attacks. So given the data users and the cloud providers are compromised, they can easily compromise the data analysis pipeline. For example, they can compromise the Spark library so that it constructs a malicious Spark plans or tests to breach the data. But also, the distributed nodes can be compromised so that even the Spark plan and task were benign, the actual execution in the nodes are compromised to breach the data. So to defend against these attacks, we secure the data analysis pipeline. So we first compartmentalize the Spark application. In the Spark application, the untrusted user's code and the Spark library runs in the same address space. So basically, we have to sandbox the user's code from compromising the Spark core components. But however, instead of employing error-prone in-memory sandboxing, we simply separate the address space so that the untrusted user code cannot compromise the Spark over the address space isolation. Then we enforce all the Spark plans constructed by the Spark application to be relayed to a trusted point in the safe address space before being executed. Then we build a distributed confidential computing environment where the entire Spark plan is executed and protected. So as you can see here, the distributed nodes are verified and connected through remote attestation, and only when such check passes, the plans are actually executed in such nodes. However, even on this secured data analysis pipeline, the untrusted data users can still violate the expectation by building the Polish violating Spark plan. So to prevent such attacks, we design our new Polish enforcement mechanism on Spark plan, which works on the pattern matching. So we provide a new Polish language for the data owners to define their expectations into the policies. So let me explain this Polish enforcement with a motivating scenario of targeted clinical trials. In this scenario, the hospital wants to share their medical data set to a pharmaceutical company. And the data set has the schema, as you can see here. So the patient table has the private information of the patient, such as name and age. And the diag table contains the history of diagnosis, such as the disease or diagnosed disease or heart rate. Given this data set, the goal of pharmaceutical company is to obtain the name and address of the patient for their targeted drug testing. On the other hand, the hospital still wants to protect the privacy of their patient. For example, they do not want to reveal who has been diagnosed with which disease. Given this expectation, benign Spark plans such as this one will be allowed because it is just analyzing the heart rate of the diagnosis and obtaining the name. However, by adding a simple filter node, it violates the expectation. So as you can see here, the filter node filters the diagnosis table based on the digits and then obtaining the name. So actually, it is exposing who has been diagnosed with cancer. To prevent such plans, we provide a Polish language for the data owners, and they can define the policy like this. So in this policy, they specify the table they want to enforce the policy, and the pattern of nodes they want to allow or disallow. So in this case, the pattern will be to filter first and then join, and to disallow such pattern. Given this policy and the plan, we enforce the policy by matching the intermediate nodes in the Spark plans against the pattern in the policy. So in this case, the pattern is matched and the plan will be denied. So we achieve both security requirements for protecting data, and we implement the compartmentalization by creating each Spark context in each side, and we build a distributed confidential computing environment using AMD CBSMP. And we design our Polish language based on the regular expression, and we match the plan using the regex matching. So to evaluate the security of our framework, we enforced 7 custom-defined policies on 22 queries from TPCH benchmark. The example policies are like this, and for example, we prevent obtaining the personally identifiable information or linking the private information and the personally identifiable information. And we also evaluate the performance of our framework. And our framework has 35% of latency and 25% of throughput overhead on average. So to conclude my presentation, we propose a new secure data analytics framework on Spark. And we believe our framework can be used for the data owners to avoid regulatory violations while sharing the data. Yes. Thank you for listening, and I will be happy to answer any questions. Yeah.
Hi, this is Kyudong from NYU. Really great talk, and I have one question for the policy definition. It looks like the work is preventing certain logical plan that
Yes.
matching some pattern. Does this work also considering policies that some records should be filtered out based on some data's condition, or after the after you're getting some computation result, then the output should be dropped?
Okay. Can you say again did you say the? Can you say again about the question?
Oh yeah, the idea is looks like all the policies demonstrated is doing pattern matching on physical plan or some plan tree. Does it also consider some data-based filtering or other condition-based policy enforcement?
Basically, it only works on the plans, on the Spark plans. So So the policy can be expressed in the plan, then we can enforce the policy, but we do not support other things.
Okay, thank you.
Any other questions? So I have a question regarding what is the role of SEV or a TE here. So how do you actually use that?
Basically, we assume the cloud providers can be compromised. So even in such environment, we have to ensure the security of our data. So we used the confidential computing.
Okay. So if there's no other questions, let's thank Jian Wang again. Thank you very much.